Hello, and welcome to the Snoozy Scientist. I'm so glad you found your way here. Whether you're winding down from a long day, quieting a restless mind, or simply love the gentle rhythm of bedtime science, this video was made just for you. Tonight, we're easing into a question that has puzzled scientists, dreamers, and storytellers for years. Is it possible to travel faster than light? It sounds simple, but the answer takes us deep into space and through the strange rules of physics. Since the beginning, humans have always chased speed. Horses, engines, rockets, each faster than the last. But what if we could outrun the fastest thing we know? What if we could go beyond the speed of light? Before we begin, I'd love to know where in the world are you listening from and what time is it right now? Are you lying in bed under the stars or winding down somewhere cozy with the hum of a distant city in the background? Maybe you're curled up on the couch with something warm in your hands, letting the day melt away. If these sleepy journeys help you relax or spark quiet wonder, I'd be truly grateful if you gave the video a gentle like and tapped that subscribe button. It helps more curious dreamers find their way here, and it means I can keep making these soft, thoughtful stories just for you. Now, I do hope this video isn't too interesting, but if it happens to keep you awake, at least you'll leave with a little more wonder than you came with, and that's never a bad thing. So take a deep breath, settle in, let your eyes rest if they want to, and let's take a slow, thoughtful journey into the mystery of light and wander through what it really means to chase the fastest thing there is and why the universe might be whispering back, not so fast. Light doesn't make much noise. It doesn't crash or roar or leave a trail of dust behind, but quietly, invisibly, it holds the record for the fastest thing in the universe. Whether it's sunlight touching your skin, the glow of a candle in the dark, or the stars twinkling far above, light always moves at the same astonishing pace: 299,792,458 meters per second. That number may feel like a jumble of digits, too big to hold in your head, but it's one of the most important numbers in all of science. It is the cosmic speed limit, a rule that nothing can break, no matter how hard it tries. Imagine, just for a moment, something that moves so fast it can circle the entire Earth more than 7 times in 1 second. That's how fast light travels. Not just sometimes, and not only when it's feeling energetic, always and everywhere. It doesn't need a boost, it doesn't lose steam, and it doesn't take breaks. Whether it's streaming from the sun, bouncing off your book, or reaching your eyes from a star hundreds of light years away, light keeps going at exactly the same speed. But what makes this speed so special? Why is it the fastest anything can go? It starts with the fact that light is a kind of wave, not like the waves in the ocean, but a wave made from electric and magnetic energy. That's why it's called an electromagnetic wave. And unlike sound or water waves, light doesn't need air or water to move. It can travel through the vacuum of space without any help at all, just pure motion through the emptiness. The strange part is that no matter how you chase it, light is always moving away from you at the same speed. If you were somehow flying through space at half the speed of light, and you turned on a flashlight, the beam wouldn't rush ahead of you at just half speed. It would still travel at full speed, 299,792,458 meters per second, whether you were standing still, flying forward, or drifting backward. It's as if the universe adjusts everything else: time, distance, motion, just to keep the speed of light the same. That one number never changes. Scientists call it a constant, and not just any constant, but a universal one. It shows up everywhere, in the equations that describe electricity, magnetism, gravity, and even the nature of space and time. In fact, the meter, the unit we use to measure distance, is now defined by how far light travels in a fraction of a second. That's how seriously we take it. We use light itself to define the ruler. But light speed is more than just fast. It shapes the rules of the universe. It decides what can happen, when it can happen, and how far information can travel. When a star explodes in a distant galaxy, its light races through space to reach us, and that journey might take millions or even billions of years. We're not seeing the explosion as it is, we're seeing it as it was, because light can only go so fast. Every time we look up at the night sky, we're looking into the past, and it's all because of that one number. Now, here's something calming to think about. This speed isn't just a limit, it's also a connection. Light lets us see, lets us know, and lets us understand what's out there. Without it, we'd be in the dark, not just physically, but completely. No pictures, no stars, no stories from across the cosmos, just silence. So while 299,792,458 meters per second may sound like a mouthful, it's really a kind of heartbeat, the steady rhythm that the universe follows, a speed that never changes no matter where you are or how fast you're going. It keeps everything in order. It keeps time flowing forward. It keeps the universe understandable. And maybe, just maybe, it's fast enough. Light doesn't try to be fast, it just is. While everything else seems to struggle against air, gravity, or friction, light moves effortlessly. It doesn't push off the ground, it doesn't burn fuel, it simply travels. And the reason it can move so quickly, the reason it reaches that unbelievable speed of 299,792,458 meters per second, is because it carries something very special: no mass at all. To understand why this matters, let's start with a simple idea. Most things you know, from a pebble to a planet, have mass. Mass is what gives things weight. It's also what makes them hard to move. When you try to push a chair across the floor, you're pushing against its mass. When a rocket lifts off the ground, most of its energy is used just to fight against the weight of its own fuel. Mass slows things down. It resists motion. But light is different. A particle of light, called a photon, has no mass, none at all. And that one simple fact changes everything. Because photons have no mass, they're not weighed down by inertia. Inertia is the tendency for things with mass to stay still or keep moving at the same speed unless something forces them to change. It's why a heavy truck takes longer to stop than a bicycle. But photons don't carry that burden. They're free from the rules that slow most things down. In fact, the moment a photon comes into existence, say when an atom gives off light, it's already moving at full speed. There's no warm up, no acceleration, no ramping up over time. It's instant. One moment it's born, and the next it's racing through space at the maximum speed the universe allows. Now, here's where it gets even more curious. According to Einstein's theory of relativity, the more mass something has, the harder it is to get it moving quickly. And as something approaches the speed of light, its mass appears to increase. It takes more and more energy just to go a little bit faster. Get close to light speed, and the energy you need becomes enormous. Try to reach it, and the energy required becomes infinite. That's right, infinite. And infinite energy is not something we have lying around. But light doesn't have this problem. Since photons have zero mass, they don't need infinite energy. They don't even need any extra energy. They naturally move at light speed, simply because that's the only speed they can move. If they were to slow down, they wouldn't just be tired, they'd cease to exist. This makes light not just fast, but uniquely fast. It's not just beating a race, it's running a race that only it can enter. It's also the reason light doesn't age the way we do. You and I experience time. We wait, we grow, we feel moments pass, but for a photon, time doesn't move. From its point of view, the moment it's created and the moment it reaches its destination happen at the same time. It doesn't tick through seconds or minutes, it just is. And while that's hard to imagine, it helps us understand why light travels the way it does. It's not just zipping through space because it wants to. It's obeying the deep structure of the universe, the laws of motion, of energy, of space time itself. Light has found the one path through these laws that lets it move freely, and it takes that path every time. You can think of it like this. Imagine a road where everything with mass needs to push a heavy cart uphill. But photons don't have carts. They don't even have feet. They simply float above the road, untouched by the weight that slows everything else down. That's why they're so fast, because they don't carry anything that would make them slow. So the next time you see sunlight on your wall or a flashlight cutting through the dark, remember what makes that light so special. It's not just brightness or warmth or glow. It's the fact that it's massless, effortless, unstoppable, a messenger of energy, moving at the one speed the universe allows for something so perfectly weightless. Light moves fast, not because it's in a hurry, but because it was never meant to slow down. Light travels fast, unbelievably fast. It zips through space at nearly 300 million meters per second, moving with a quiet confidence that nothing else can match. And as much as we might dream about catching up, or even passing it, there's a problem, a very big one. We can't, and the reason is simple. We have mass. Light doesn't, and that changes everything. Mass is what makes things heavy. It's what gives things substance. A rock has mass. So does your body, your car, your cat, and every spaceship we've ever built. Even the tiniest grain of sand has mass. It's what pulls things down to Earth and keeps planets circling the sun. But it also makes motion harder, because the more mass something has, the more effort it takes to get it moving. When something has mass, it doesn't want to move without a push. And once it's moving, it doesn't want to stop. That's inertia. It's like trying to roll a bowling ball across a floor. It takes effort to start. It takes effort to stop. Mass is the reason why. Now, imagine you want to speed up. At first, it's easy, a little force, and you go a little faster. But the faster you move, the harder it gets. Not because you're getting heavier in the usual way, but because the universe starts to resist. According to Einstein's theory of relativity, as you get closer to the speed of light, your mass doesn't stay the same, it begins to increase. Not by much at first, but as you go faster and faster, your mass grows, and with it, the energy needed to keep speeding up grows too. Let's say you're flying through space in a very fast spaceship. You push the engines harder, your speed increases. You push again and again, but each time you need more energy than before, because now it's not just your speed that's growing, it's your mass. And if you keep trying to reach the speed of light, your mass keeps increasing. Eventually, it becomes so large that it would take more energy than exists in the entire universe just to go a little bit faster. And then you hit the wall. Not a physical wall, but a limit. That limit is light speed. You can get close, very close, but no matter how hard you try, no matter how powerful your engine is, you'll never reach it, because to do so would require infinite energy. And infinite energy isn't something we have. It isn't something we can have. It doesn't exist in any real usable way. Light doesn't have this problem. It has no mass. That's why it can travel at its incredible speed without effort. It doesn't need to push. It doesn't gain weight as it moves. It doesn't face resistance from inertia. It was born moving at the universe's maximum speed, and it will continue moving at that speed forever. But for anything else, for anything with mass, the rules are stricter. The universe has drawn a clear line in the sand, this far and no farther. You might wonder why the universe is built this way. Why have a limit at all? Why not let things go as fast as they want? The truth is, this speed limit keeps the universe in order. It protects cause and effect. It stops time from getting tangled. It makes sure that one event leads to the next in the right order. If we could move faster than light, we might be able to send signals into the past. We could cause effects before the cause ever happened. That would break everything we know about time and logic. So, in a way, this limit is a gift. It keeps things simple, predictable, understandable. And even though we can't keep up with light, we can still learn from it. We can study it, measure it, and watch as it brings us images from the edge of the universe. Maybe it's not about catching up. Maybe it's about listening. Light isn't just fast, it's patient. It brings us news from distant stars, carries color to our eyes, and fills our world with wonder. And as we watch it go by, quiet, steady, and impossibly quick, we're reminded that speed isn't everything. Sometimes, just understanding why we can't keep up is the first step to understanding why the universe works at all. Albert Einstein didn't set out to become a legend. He was just a young man with a quiet mind, working at a patent office in Switzerland, staring at the world and asking questions that no one else thought to ask. One of those questions was very simple. What would it feel like to ride alongside a beam of light? That one thought opened the door to an idea that would change everything, an idea now known as special relativity. Special relativity sounds like a big term, but at its heart, it's built on just a few simple truths. The most important one is this: the speed of light is always the same. No matter how fast you're moving, no matter where you are, no matter what direction you're going, the speed of light never changes. It's always close to 300 million meters per second. And when half mass per watts, before Einstein, people thought speed worked like stacking blocks. If you're walking on a moving train and the train is already going forward, then your total speed is your walking speed plus the speed of the train. And for everyday things like cars or bicycles or baseballs, that's true. But light doesn't work that way. But imagine you're on a spaceship moving incredibly fast, almost at the speed of light. You turn on a flashlight and watch the beam travel forward. You might think, since the ship is already moving, that the beam should go faster than normal, but it doesn't. Even from the outside, watching from another spaceship or from Earth, that beam of light is still moving at the exact same speed it always does, the same speed it would have if the flashlight were standing still. That was the puzzle, a strange, surprising, beautiful puzzle. Einstein realized that the only way to make this work was to let go of something we always thought was fixed, the idea that time and space are the same for everyone. He discovered that in order for the speed of light to stay the same for all observers, the universe has to stretch and squeeze the way we experience time and distance. In other words, time and space are not fixed, they are flexible. They bend to keep the speed of light locked in place. So, what does that really mean? And it means that time can slow down. If you're moving very fast close to the speed of light, time for you will pass more slowly compared to someone who is standing still. This is called time dilation. It sounds like science fiction, but it's very real. We've tested it. Astronauts on the International Space Station moving quickly in orbit, actually experience time a tiny bit more slowly than people on Earth. It also means that distances can shrink. This is called length contraction. If you were moving near light speed, the distance in front of you would seem shorter than it would to someone not moving. Again, this is not a trick of your eyes, it's built into the fabric of the universe. And there's more. Two people moving at different speeds may disagree on whether two events happened at the same time. For example, imagine lightning strikes the front and back of a train at the same moment. Someone standing on the platform might see them happen at once, but someone riding the train might see one first and the other later, and both people would be right. Because in special relativity, simultaneity, the idea that things happen at the same time depends on your motion. All of this may sound strange, and it is, but it's also incredibly elegant, because out of this puzzle came a new understanding of reality, one that works not just in theory, but in practice. It explains why particles behave the way they do in high speed labs. It explains how GPS satellites must adjust their clocks to stay accurate. It explains the heartbeat of the universe, a rhythm that light keeps steady, no matter what. Einstein didn't break the rules, he uncovered them. He showed us that the universe isn't built on fixed frames and rigid clocks. It's built on relationships between time, space, motion, and energy. Light moves the same speed for everyone, and because of that, everything else must flex to keep up. So the next time you turn on a flashlight or watch sunlight break through the clouds, remember this: you are witnessing something that not only moves faster than anything else, but something that follows one of the deepest, most beautiful truths in all of physics. A truth that says no matter who you are or how fast you're going, light will always meet you at the same pace. And maybe that's the most comforting part of all. In a world where so much can shift and change, there's one thing that stays steady. Light doesn't rush for anyone. It doesn't slow down. It simply is, a constant guide in a flexible universe. That's the elegance of Einstein's puzzle. Simple, strange, and quietly perfect. Getting close to the speed of light is like stepping into another world, one where the rules you've always known begin to shift, stretch, and change. Things don't behave the way we're used to. Time slows down, mass grows heavier, distances shrink. The closer you get to light speed, the stranger everything becomes. Let's imagine for a moment that you're on a spaceship. Not just any spaceship, but one capable of reaching speeds close to the speed of light. Maybe not all the way there, but far beyond anything humans have ever built. As you accelerate, you don't just feel faster, you feel reality itself start to bend around you. The first thing you notice is time. On board your ship, time feels normal. You're reading a book, sipping some tea, watching the stars drift by. Everything seems calm and familiar. But outside your ship, things are changing. Clocks on Earth are ticking faster than yours. If someone were watching you from the ground, they'd see your time moving slowly, like a movie in slow motion. This is called time dilation. It's not an illusion, it's not a trick, it's a real effect built into the way the universe works. The faster you move, the slower time flows for you compared to someone standing still. If you flew close to the speed of light and came back to Earth, you might find that only a few years passed for you, but many more passed for everyone else. We've even tested this. Tiny particles called muons are created high up in Earth's atmosphere by cosmic rays. These particles live for a very short time, just microseconds before they decay. But when they're moving close to the speed of light, they live much longer, long enough to reach the ground and be measured. Their clocks, in a sense, slow down as they speed up. That's time dilation in action. Now let's look at mass. As your spaceship accelerates, something else begins to happen. You start to feel heavier, not in the normal sense, not like you've eaten too much dessert, but in the way your mass responds to motion. As you get faster, your mass increases, not because you're gaining matter, but because the universe starts resisting your speed. Think of it like trying to push a sled across ice. At first, it slides easily, but the faster you try to go, the harder it becomes to push. The sled seems to fight back. That's what happens with mass near light speed. The faster you go, the more energy it takes to keep accelerating, and as you get closer to the speed of light, your mass grows so large that it would take infinite energy to go any faster. That's the hard limit, the wall we can never break, because no amount of fuel, no burst of power, no clever trick can overcome infinity. It's the reason no object with mass can ever reach the speed of light. And there's more. Distance begins to warp too. If you're flying toward a distant star, the space in front of you starts to contract. The journey, from your perspective, becomes shorter. This is called length contraction. It means that while someone watching from Earth might say the star is 10 light years away, your ship might experience that distance as much smaller. To you, it feels like the universe is folding in, making room for your motion. The faster you move, the more space compresses in the direction you're heading. Again, this isn't imagination. It's not a weird camera effect. It's built into the way space-time behaves near light speed. So what does all of this mean? It means the universe protects its speed limit in a very elegant way. It bends time, increases mass, and compresses space, all to make sure that nothing with mass can ever catch up to light. Everything works together to keep light's pace locked in place. And while this might sound like a barrier, it's also kind of beautiful. These effects, time slowing, space shrinking, energy growing, are not problems. They are the way reality responds to motion. They are the signs that we live in a flexible universe, one that stretches and flows instead of snapping or breaking. It also means that if we ever want to travel to the stars, we'll need to understand these effects deeply, because the closer we get to light speed, the more our journeys will feel different from what we're used to. We'll need new ways of thinking, new ways of measuring, new ways of dreaming. But for now, we can simply marvel at what happens near light speed. Time stretches, mass grows, space bends, and through it all, light keeps moving at its perfect steady pace, the same for everyone, everywhere. It's a reminder that speed isn't just about motion, it's about how the universe breathes, shifts, and makes room for what's possible. And maybe, just maybe, it's telling us something gentle, that going faster means letting go of how we thought things should work and learning how they do. Not all journeys need to arrive. Some are just about understanding the path. It's a simple thought. Just go faster, add more fuel, push the throttle a little harder. After all, when you want to speed up your bike or your car or even a rocket, you just add more power. But when you start approaching the speed of light, that simple thought runs into something strange. It's not just harder to go faster, it becomes impossible. Not because we don't have the right tools yet, but because the math says so. To go faster than light, you'd need infinite energy, and the universe simply doesn't allow that. Let's start with a slow, gentle picture. Imagine you're floating in space, far from any planets or stars. You fire up your spaceship. At first, things go as expected. You speed up, double your speed, and you need more fuel. Double it again, and you need even more. But everything still makes sense. Then you start moving faster, much faster, closer and closer to the speed of light. And now, something starts to feel different. Every bit of extra speed takes more effort than the last. You keep pouring in energy, but your speed increases by less and less each time. This isn't just a mechanical problem. It's not a matter of engine strength or clever design. It's built into the fabric of space and time. According to Einstein's theory of relativity, as an object with mass speeds up, its energy goes up, but not just gradually. The energy curve rises sharply. At first, it's gentle, but the closer you get to light speed, the more the curve tilts upward, like a mountain that keeps getting steeper. And then, just before you hit the speed of light, the curve shoots up to infinity. This is what physicists call an asymptote, a limit you can get close to, but never actually reach. No matter how much energy you put in, you'll never cross that final line, because the energy you'd need to do so isn't just huge, it's infinite. And infinite energy doesn't exist. Think of it like this: if someone gave you $1 every second, you'd get richer over time. If they gave you $1 million every second, you'd be richer still. But if they told you they'd give you infinite money, well, they'd never finish. You'd never receive all of it because infinite means never ending. It's not just big, it's unreachable. Now apply that to speed. To push a spaceship past the speed of light, you'd need more energy than exists in all the stars. Then more than that. Then more still. And still, it wouldn't be enough. You'd be chasing a goal that keeps moving out of reach, no matter how far you go. And here's the deeper truth. The reason you need infinite energy is because your mass increases as you get faster. Not in the way your weight changes with gravity, but in how much resistance your body has to motion. The faster you go, the more energy it takes just to keep going, and even more to go faster. As your speed rises, your mass rises too. At light speed, your mass would become infinite, and to move something with infinite mass, you need infinite energy. So it's not just difficult, it's not just a challenge, it's a wall, a solid boundary the universe has built into the rules of reality, a speed you can approach but never pass. You might wonder, why does the universe work this way? Why draw such a hard line? And while we may not know all the answers, there's beauty in this rule. It keeps things stable. It keeps cause and effect in the right order. It stops chaos. If anything could move faster than light, strange things could happen. Messages could arrive before they were sent. Events could unfold in reverse. The story of the universe would get tangled and confused. So the limit is not just a barrier, it's a kind of protection, a quiet law that makes the universe make sense. And perhaps that's why the idea of infinite energy feels so unnatural. Because the universe likes balance, it allows incredible speed, it allows massive power, but not without limits, not without cost. We can build ships that go fast. We can imagine journeys to other stars. But when we dream of faster than light travel, we're dreaming beyond what energy and space and time will allow. And maybe that's okay. Maybe we don't need to break the rules to find wonder, because even at slower speeds, we still explore, we still discover, we still reach for the stars. So the next time you think about light speeding through space, remember what makes it so unique. It doesn't need infinite energy. It doesn't need anything at all. It simply moves effortlessly, gracefully, always at the same perfect pace. And for the rest of us, with our mass, our effort, and our dreams, it's a reminder that some limits aren't meant to be broken, they're meant to be understood. Let's take a gentle step away from what we know and wander for a moment into the world of what if. Not all science is about what we can see and measure. Sometimes it begins with a strange idea that makes us pause and wonder. One of those ideas is a particle called the tachyon. Tachyons are not something you'll find in a lab or tucked inside a telescope. They're hypothetical, which means they only exist on paper, inside equations, and in the minds of physicists who enjoy chasing mysteries. But they're fascinating because if they were real, they would break one of the most sacred rules in the universe. Tachyons would always travel faster than light. Now that sounds exciting. After all, the speed of light, nearly 300 million meters per second, is supposed to be the limit, the cosmic speed cap, the boundary nothing can cross. But tachyons don't try to break that limit by speeding up. In theory, they're born on the other side. They don't slow down to reach light speed. They start out faster, and they can never slow down enough to reach the speed of light from above. It's a bit like running a race where you're always ahead, but never able to stop or even meet the people behind you. You don't cheat to get in front, you simply start from a different place altogether. Tachyons first appeared in the 1960s as a mathematical curiosity. Physicists noticed that certain versions of their equations allowed for particles with imaginary mass, and not imaginary as in pretend, but imaginary as in a number involving the square root of -1. That kind of math is strange and hard to picture, but in those equations, a particle with imaginary mass could move faster than light without ever breaking the laws of relativity. That's because relativity doesn't actually forbid faster than light travel in theory. What it forbids is crossing the light speed boundary. Anything slower than light can never speed up past it, and anything faster than light, like a tachyon, could never slow down below it. It's a one-way street on either side. But just because the math allows something doesn't mean it's real. Tachyons are fascinating on paper, but in the real world, we've never seen any sign of them. Not in particle accelerators, not in cosmic rays, not in the background noise of the universe. If tachyons existed, they might leave behind unusual signals, strange energy patterns, or odd effects on other particles. But so far, the universe has been quiet. And if tachyons did exist, they would raise more questions than answers. Because moving faster than light means more than just being fast, it means playing tricks with time. In special relativity, when something moves faster than light, it can appear to arrive before it leaves, depending on who's watching. That's a problem, because it breaks causality. It means the effect could come before the cause. It means a message could be received before it was sent. It means time as we understand it would stop making sense. And that's not just uncomfortable, it's dangerous for the logic of the universe. This is one reason many physicists are cautious with ideas like tachyons, not because they dislike imagination, but because science is built on consistency, and faster than light particles would create ripple effects that tear holes in the order of events. Even so, the idea of tachyons still holds a certain charm. They show us how flexible our theories are. They remind us that our equations sometimes stretch beyond the visible into places we've never been. And even if those places turn out to be empty, they still help shape the questions we ask next. Some people have even tried to use tachyons in science fiction. In those stories, they become tools for sending messages across space instantly, or even communicating across time. They're like the magical shortcuts of physics, the imagined answer to the question, what if we could go faster than light? But as far as real science goes, tachyons remain silent. No signals, no proof, no whispers from the other side of the speed limit. And maybe that's the answer. Maybe the speed of light is not just a line to be crossed. Maybe it's a border for a reason, a gentle boundary that keeps time moving forward, that protects cause and effect, that lets the universe tell its story, one page at a time. So while tachyons may be fun to imagine, racing endlessly ahead, always just out of reach, they are, for now, invisible. Not because we haven't looked hard enough, but because they may never have been there to begin with. And that's okay, because sometimes understanding why something likely doesn't exist can teach us just as much as discovering something new. In chasing tachyons, we learn the shape of what is real. And in that quiet space beyond light's reach, the universe still holds its rhythm, constant, predictable, wonderfully complete. Some ideas in science sound so strange, they feel more like magic than math. And one of the strangest of all is something called quantum entanglement. You might have heard it described as spooky action at a distance. That was Albert Einstein's name for it, and even he wasn't sure what to make of it. Entanglement is real. It's been tested, it's been measured, and it works, but there's a common misunderstanding that comes along with it. Some people think entanglement could be a way to send messages faster than light, a secret shortcut through space, a kind of instant communication line between two particles, no matter how far apart they are. But as fascinating as that sounds, the truth is more subtle and even more beautiful. So let's take it slowly. Imagine you have a pair of tiny particles. These could be photons, or electrons, or any little piece of the quantum world. In a special setup, you can link them together in a way that connects their properties. This is what scientists call entanglement. Once the particles are entangled, something curious happens. Whatever you do to one seems to affect the other instantly, even if they are far apart. You could place one particle on Earth and send the other to the moon, measure something about the one on Earth, and the other will seem to know the result right away. No waiting, no signal delay, no light speed limit. It sounds like magic, or at least like science fiction. But here's the key detail. While the particles are connected, we cannot control what result we get when we measure one. The outcome is random. It's not like sending a message that says yes or no. It's like flipping a coin. You can flip it in New York and get heads, and your friend flips theirs on the moon and gets tails. The results are opposite, just as expected, but neither of you could choose the outcome ahead of time. Because of that, there's no way to use entanglement to send information. You can't send a signal. You can only compare results after the fact. And when you do, you'll find they match in a very specific and eerie way. But until you check, the pattern stays hidden. So, why does this matter? Because the universe still respects its own speed limit. Even in the strange world of quantum physics, the rule stands: nothing with mass and no usable information can travel faster than light. Entanglement feels instant, but it cannot be used to communicate. It's like a whisper that carries no words. Einstein didn't like that. He believed there had to be something missing, some hidden mechanism that would explain the connection. But over time, experiments showed that no hidden variable could account for what was happening. The connection between entangled particles is real. It is not a trick, it is not a delayed reaction, but it is not a shortcut either. You can think of it like two spinning tops created in a special way. If one is spinning clockwise, the other must be spinning counterclockwise. They were set up that way from the beginning. You spin one and see it go right, and the other goes left. No message had to be sent. No rule was broken. But in the quantum world, it's even stranger. The tops do not have a definite spin until you measure them. It's as if they decide in the moment and yet still agree across any distance. It's no wonder people get excited about this. The idea of instant connection is so powerful. We want it to mean more. We want to imagine calling someone across the galaxy and hearing their voice right away. We want a bridge through space, but entanglement is not that kind of bridge. It is a mirror, not a messenger. And in a way, that makes it more mysterious, because it shows us that the universe is connected in ways we don't fully understand, but not in ways we can use to cheat the rules. It's as if nature gives us a glimpse of something deeper, then quietly closes the door. So while entanglement won't let us outpace light, it does remind us that the universe is full of surprises. It tells us that the smallest things can be tied together across the largest distances. It tells us that separation may not be as simple as it seems, and it tells us that even when things appear random, there may be patterns underneath, waiting to be revealed. But for now, no instant messages, no faster than light travel, no shortcut through the stars, just a quiet connection, a spooky little dance between particles, and a gentle reminder that the universe still keeps its secrets, even as it invites us to keep asking. So when someone tells you that quantum entanglement could let us send messages instantly across space, you can smile and say, it's weirder than that, but not quite that fast. Not everything about light is what it seems. Just when we think we understand its limits, the universe gently reminds us that the rules, while firm, can bend in surprising ways. We've said that nothing can travel faster than light, and that's true, but with a small, important detail. Nothing can travel faster than light in a vacuum. A vacuum is empty space. No air, no dust, no water, just nothing. And in that perfect emptiness, light travels at its full speed, nearly 300 million meters per second. That's the fastest anything can go, and nothing with mass can ever catch up. That's the rule. But what if we're not in a vacuum? What if we're underwater, or moving through glass, or walking through air? In those places, light slows down, just a little in air, a little more in water, and even more in something thick like glass or plastic. Not because it's tired or losing energy, but because it has to interact with the atoms in those materials. It gets absorbed and re emitted, nudged and jostled, over and over again. It's like a person weaving through a crowd, still headed forward, but not in a straight line. So while light always tries to move at its top speed, the medium it moves through slows it down, not permanently, and not in a way we can always see, but enough to change how it behaves. And that's where something very interesting happens. If light slows down in water and we send a charged particle, like an electron, into that same water at just the right speed, it's possible for that particle to go faster than light's speed in that medium. It doesn't go faster than light's top speed in a vacuum. That rule still holds, but it moves faster than light can in water. When that happens, something beautiful and strange occurs. A faint blue glow begins to appear. It's called Cherenkov radiation. You've probably seen this glow before, at least in photos. It shows up around nuclear reactors submerged in water, a soft, eerie blue that seems to hum with energy. It's not from heat or burning or any kind of flame. It's the light given off when a charged particle outruns light's local speed, not the universal limit, but the slowed down version that light is stuck with in that particular place. It's a bit like a sonic boom, but with light instead of sound. When a jet breaks the sound barrier, it creates a shock wave, a clap of pressure that ripples through the air. It's not that sound has stopped working, it's that the plane is moving faster than sound can travel in that space. Cherenkov radiation is the same idea, but with light. The charged particle disrupts the electromagnetic field around it as it moves, and because it's going faster than light can in that space, it creates a kind of optical shock wave. The result is that signature glow, silent, soft, and unmistakably blue. This isn't breaking the laws of physics. In fact, it proves them because the universe always makes sure the rules are followed, even when it allows for clever workarounds. The particles that create Cherenkov radiation are still obeying the ultimate speed limit. They're not faster than light in a vacuum, they're just faster than light in water or whatever material they're passing through. And that difference matters because it shows us that speed isn't just about what you're moving through space, it's also about what space is made of. Light isn't a fixed runner on a cosmic track, it's part of the terrain itself, shaped by what it passes through. So when we see that glowing blue light, we're not witnessing a broken rule, we're witnessing a local exception, a place where the conditions shift just enough to let a particle momentarily win the race. It's humbling, really. Even in a universe built on firm constants and hard limits, there are still gentle ways to surprise us, still hidden doors that open when we least expect it. And sometimes, the light that shows us those secrets isn't from a star or a lamp, but from a particle moving just a little too fast for its surroundings. So the next time you see that soft blue shimmer in an image of a reactor, or read about particles zipping through water faster than light can follow, remember this is not a loophole, it's a local miracle. A reminder that even fixed laws have nuance, that physics is not just strict and silent, but elegant and alive. Cherenkov radiation is light, playing catch up. It is proof that even when you can't beat the universe's top speed, you might still find a way to lead, if only for a moment, and only where the rules allow. And in that blue glow, we get to witness one of nature's quietest thrills, the thrill of almost. And some dreams are too powerful to let go of. Even when the math says no, the imagination says, what if? One of those dreams is faster than light travel, the ability to go from one star to another without spending decades or centuries floating through space. It shows up in science fiction all the time: warp speed, hyperspace, jump drives. But is there any real science that hints at such a thing? Surprisingly, yes, it's called the Alcubierre drive. And while it's purely theoretical for now, it offers a strange and wonderful idea, one that might let us move faster than light without actually moving faster than light. With Let's step back for a moment. Albert Einstein's theories tell us that nothing with mass can travel faster than light. It would take infinite energy. The universe has a speed limit, and we can't break it. That's the rule. But there's a difference between moving through space and changing the space around you. That's where the warp drive idea comes in. In 1994, a physicist named Miguel Alcubierre proposed a concept that didn't break the rules of relativity. Instead, it tiptoed around them. He imagined a spacecraft that didn't accelerate in the usual way, but instead sat inside a bubble of space. The bubble itself would move, not the ship. Picture it like this: imagine space is a giant rug. Normally, to move across the rug, you'd walk, but what if you could stay still and fold the rug around you? You're not running over it, the rug is moving beneath you. You haven't broken the speed limit, you've changed the road. The Alcubierre drive works like that. The idea is to contract space in front of the ship and expand it behind. The ship stays inside a flat zone in the middle, untouched by acceleration, but the space around it warps like waves rippling on a pond. The bubble moves, and so does the ship inside it. To an outside observer, it would look like the ship is moving faster than light, but technically it isn't. It's the space that's moving, and because space itself isn't bound by the speed limit, the rules stay intact. It's a brilliant idea, and it raises fascinating possibilities. With a warp bubble, You could travel from Earth to a distant star in what feels like no time at all. You could cover light years without aging much. Time would behave differently inside the bubble than outside. And the best part? The ship wouldn't experience the crushing effects of acceleration. It would just float in a pocket of calm, carried along by the shape of space. But here's the catch. There's always a catch. To make this kind of drive work, you would need something called negative energy. Not just regular energy, the kind that powers engines or lights up cities, but something stranger, something that repels rather than attracts. Scientists call it exotic matter, and while some quantum theories suggest it might exist in tiny amounts, we have no idea how to create it, let alone control it in the quantities needed to bend space itself. Then there's the question of stability. Even if you could generate a warp bubble, how would you steer it? How would you stop? How would you make sure it didn't collapse or tear apart everything nearby? And finally, there's the issue of causality. Some versions of the warp drive might allow for time travel or create paradoxes we can't fully predict. That makes physicists nervous. Nature tends to protect its timelines. So for now, the Alcubierre drive remains a beautiful thought experiment, a reminder that even within strict rules, creativity has room to breathe. Still, the fact that such an idea is even allowed by Einstein's equations is remarkable. It tells us that space is not just empty, it's flexible, stretchable, alive in a way we're only beginning to understand. Maybe one day we'll learn how to shape it. Not by brute force, but with elegance, the way you shape wind with sails or water with a canal. And maybe, long from now, someone will look out a window and see the stars blur as their ship folds space around them. No fire, no explosion, just a quiet hum as the bubble glides through the cosmos. Until then, we can keep dreaming, because dreaming is where science begins. And who knows, maybe the universe is waiting for us to learn how to fold its rug, not to break its rules, but to understand them so well that they lead us forward, not faster, but smarter. That's the heart of the warp drive, not a shortcut through space, but a deeper understanding of what space really is. Let's imagine for a moment that you have the blueprint for a warp drive sitting in your lap. The math checks out. The design is elegant. The ship doesn't need to push itself through space. It simply folds space around it. You could travel from Earth to another star in the time it takes to sip a cup of tea. But there's one big problem sitting right in the middle of the plan, a missing ingredient, the kind that's not found in any lab or mined from any planet, a kind of energy we're not even sure exists in any usable form. It's called exotic matter. Exotic matter sounds like something out of a science fiction novel, and honestly, right now that's where it mostly lives. But in theory, it's a real thing. Not something made up for fun, but a serious part of the equations that describe how the universe might allow for a warp drive. To understand why we need exotic matter, we have to look at what a warp drive actually does. It doesn't make your ship go faster than light. Instead, it changes the shape of space itself. It compresses space in front of you and stretches it behind you, like pushing down one end of a trampoline and lifting the other. You're not speeding through the trampoline is shifting beneath you. That's all fine in theory, but bending space like that requires something that behaves in a very unusual way. Ordinary matter, like the stuff you and I are made of, has positive energy. It pulls things together. Gravity, for example, comes from mass attracting mass. It makes space curve in predictable ways. Exotic matter would do the opposite. It would have negative energy, which means it would push space apart. It's the only way to create that strange warp bubble, with expansion behind and contraction in front. Without exotic matter, the bubble collapses. The ride ends before it ever begins. So, where do we find this mysterious substance? Well, we don't. Not yet. That's the heart of the problem. And some forms of negative energy have been hinted at in the world of quantum physics. Tiny effects like the Casimir effect suggest that empty space isn't really empty. There's a quantum buzz in the background, particles popping in and out of existence, creating fluctuations that briefly behave like negative energy. But these effects are tiny, so small that you could barely measure them, and they only happen under very specific conditions. Even if we could isolate that kind of energy, we'd need an enormous amount of it to power a warp drive. Not a teaspoon, not a truckload. We're talking about enough exotic matter to surround a spaceship and manipulate the fabric of space itself. Right now, that's far beyond anything we can produce, let alone control. And there's another issue. Exotic matter, if it exists in large quantities, might be extremely unstable. It could react in ways we don't fully understand. It might create risks we can't predict. After all, this is a substance that defies the usual behavior of the universe, that makes it fascinating, but also dangerous. And even the equations that suggest exotic matter might be possible come with heavy caveats. They depend on ideal conditions, perfect symmetries, and sometimes even assumptions that may not hold up in the real world. As our understanding of physics grows, some scientists wonder if exotic matter might always remain a mathematical ghost, allowed in theory, but impossible in practice. Still, we keep looking because the idea of folding space, of hopping from one star to another, is just too powerful to ignore. And who knows, science has a habit of surprising us. There was a time when antimatter was purely theoretical, when black holes were just curious predictions, when lasers were considered useless. Today, they're all real. Maybe exotic matter will join that list. Maybe we'll find a way to create it safely, to store it, to use it. But for now, the exotic matter problem keeps warp drives firmly in the realm of science fiction. A beautiful idea with a missing piece. And yet, there's something comforting in that, because it means there are still mysteries to solve, still puzzles that challenge the brightest minds, still wild, strange doors in the universe waiting to be unlocked, not with brute force, but with careful thought and patient curiosity. So if you ever feel discouraged by limits, remember this: the speed of light may be a wall, but exotic matter is a window we haven't opened yet. And that means the story's not over. Not by a long shot. Close your eyes for a moment and picture space not as a giant emptiness, but as something more flexible, like a soft sheet stretched out in all directions. Now imagine folding that sheet so that two distant points touch. What if instead of traveling across the surface, you could simply step through from one side of the universe to the other in a blink? That is the basic idea behind a wormhole, a shortcut through space and time, a hidden tunnel in the fabric of the universe. It sounds like magic, but it is rooted in real physics, at least on paper. Wormholes, also called Einstein-Rosen bridges, first appeared in the mathematics of general relativity. They were a solution hidden deep in the equations that describe how gravity bends space. In theory, if space can stretch and curve, then it might also be able to fold and connect in unexpected ways. Like a tunnel connecting two faraway cities, a wormhole could let you jump from one point in space to another without crossing the space in between. Think of it like this: if our universe were a piece of paper, you could draw two dots far apart and draw a long line connecting them. That's the usual way we travel. But if you fold the paper so the dots touch, suddenly the journey is almost nothing. A shortcut through the folds, a bridge from here to there. Sounds amazing. But as with all things that sound too good to be true, wormholes come with their own set of wild problems. First, there's the question of existence. We've never found a wormhole in real life. No telescope has spotted one. No spacecraft has drifted near one. They are entirely theoretical, ideas that emerge from the math but remain invisible in the sky. Then there's the issue of stability. Most wormholes, according to the math, would collapse instantly, like a tunnel made of sand. They would pinch shut the moment anything tried to pass through, even light. To keep a wormhole open, scientists believe you would need, you guessed it, exotic matter, the same strange substance that might make warp drives work. Exotic matter would create a kind of outward pressure, fighting against the natural tendency of space to close the tunnel. But as we've explored, exotic matter is still a mystery. It might exist only in tiny flickering amounts. It might not be usable at all. Even if you could build a stable wormhole, guiding it would be another challenge. Where does the other end go? Can you aim it? Can you anchor it near a star or a planet? Or does it drift somewhere in the cold dark? Would stepping through one feel instant? Or would it twist time as well? And then there are the paradoxes. Some wormhole models allow for time travel. If one end moves differently through time than the other, say near a black hole, or moving at high speed, it could allow a person to travel not just through space, but into the past. That opens doors to questions we don't yet know how to answer. Could someone change history? Could events loop endlessly? Could two versions of the same person meet? These aren't just science fiction questions, they challenge the very structure of cause and effect, something the universe seems to guard carefully. Many physicists believe that nature would find a way to prevent paradoxes, perhaps by making wormholes inherently unstable, or by canceling out their strange effects before they could become a problem. Still, wormholes continue to capture the imagination. They appear in movies, books, and daydreams. They offer a kind of hope that the universe might have hidden doors we simply haven't opened yet. That space, for all its vastness, might not be as lonely or unreachable as it seems. It's comforting, in a way, to know that even within the strict rules of physics, there are whispers of possibility, tiny cracks in the surface where wonder leaks through. Maybe one day, with new tools and deeper understanding, we'll find evidence of a real wormhole. Maybe it will be small and fleeting, or maybe it will stretch like a thread between stars. Maybe we'll even learn to build one, to create a tunnel from here to there, not with brute force, but with quiet knowledge. For now, wormholes remain part of the universe's secret language, a clue that there's more to space than distance and darkness, a reminder that what seems impossible today might only be waiting for tomorrow's understanding. And if they do exist, even just one, it means the universe is not just strange, it's connected in ways we can barely begin to imagine. For as long as we've looked up at the stars, we've wondered what it would be like to visit them, to fly among distant galaxies, meet strange new life, and explore worlds beyond imagination. But space is big, too big for rockets and fuel tanks, too wide for human lifetimes. So we turn to stories. Boo! And in those stories, we found ways to move faster than light. Science fiction has always been the playground for impossible ideas. It lets us ask, what if, without needing the math to work, at least not yet. And over the years, it has given us some of the most beloved ways to beat the cosmic speed limit, not by breaking it directly, but by bending the rules in clever ways. Let's start with one of the classics, warp speed. Popularized by shows like Star Trek, warp speed isn't about making a spaceship go faster than light. It's about bending the space around the ship. Instead of pushing through space, the ship rides a wave, compressing space in front of it and expanding it behind. This is actually based on a real theoretical idea called the Alcubierre drive, which you may remember from an earlier chapter. In the world of fiction, warp speed lets starships cruise between planets in minutes, all while giving the audience just enough science talk to make it feel possible. Then there's hyperspace, another favorite, especially in the Star Wars universe. Hyperspace is often imagined as a separate dimension that exists alongside our own. When a ship jumps to hyperspace, it's not traveling faster in our universe. It's moving through this other realm, where distances are shorter or space behaves differently. The idea is simple. If you can't go faster than light here, go somewhere else where the rules are different. Hyperspace is wonderfully vague. It's usually filled with glowing tunnels, streaking stars, and dramatic countdowns. It does not need to explain how it works, only that it does. It lets heroes arrive just in time. It turns interstellar war into something with pace and urgency. It makes space travel feel less like sailing across an endless ocean and more like hopping between cities. Teleportation takes an even bolder step. Why move through space at all when you can simply disappear from one place and reappear in another? In shows like Star Trek, teleportation happens through devices like transporters, breaking you down into energy, sending that energy to a new location, and reassembling you on the other side. It's instantaneous, clean, no spaceflight required. Of course, teleportation raises all kinds of questions. Is the reassembled version still you? What happens if something goes wrong in transit? What if two versions arrive at once? But fiction rarely lingers on these worries. It moves fast, just like its technology. In the story, what matters is the effect. The character was here, now they're there. No ship, no travel, no waiting. Other forms of faster than light travel appear across hundreds of books, movies, and games. And some stories use jump drives, engines that leap ships between fixed points in space. Others rely on wormholes that open like doors between distant places. Some use quantum tunneling, or space folding, or even dimensional portals. The names change, but the idea stays the same. Find a way to outsmart the universe's rules, at least for the length of a chapter. What makes these fictional technologies so powerful is not their scientific accuracy, but the emotions they carry. They make the universe feel accessible. They turn the vast unknown into a place where people live, love, and lose. They give us hope that maybe someday we will go beyond our little world, not slowly, not with limits, but freely and fast. And strangely enough, fiction has a way of nudging science forward. The idea of a satellite was once science fiction. So were submarines, video calls, and tablets. Writers imagine things, and sometimes engineers try to make them real. Even if warp drives and hyperspace never leave the page, the dreams behind them can inspire real exploration, real missions to the moon, to Mars, and maybe one day beyond. So as you drift off tonight, let your mind wander into those star streaked skies. Picture yourself on a bridge of a quiet ship, hearing the soft hum of the engines. Maybe the captain calls for warp speed. Maybe the navigator plots a hyperspace course. Maybe, without a sound, you simply vanish, reappearing on a blue planet no one's ever seen. These are stories, yes, but they're also seeds, little sparks of wonder that remind us what it means to dream big. And who knows, the universe may have rules, but humans have imagination. and that too travels fast. And there's something quietly powerful about a story, a tale whispered before bedtime, a novel read by flashlight under the covers, or a movie watched in a darkened room with eyes wide open. Stories shape us, and sometimes they shape the future, especially when they begin with a question like, what if? Science fiction has always lived in the space between curiosity and possibility. It asks bold questions. What if we could talk to someone on another planet? What if machines could think? What if we could travel across time or visit distant stars? These ideas, wrapped in imagination, seem like fantasy, but over time, some of them have nudged reality forward. Let's start with satellites. With back in 1945, a science fiction writer named Arthur C. Clarke wrote an article proposing that satellites placed in orbit could be used for global communication. At the time, it was just a clever idea, one of many in the world of speculative fiction. But today, satellites are everywhere. They power your GPS, your weather updates, your video calls. The world listened to that what if and turned it into something real. Then there's the idea of tablets and voice assistants. In the original Star Trek series from the 1960s, crew members used flat touchscreen devices to read data and communicate with the ship. They talked to the computer and received calm, intelligent responses. It seemed like magic then. Now we carry tablets in our backpacks. We ask Alexa or Siri to play music or set timers. These aren't perfect copies, but the spirit is there. Technology born in the imagination, then gently brought to life. Even the flip phone, once a marvel of portable design, was inspired by the Star Trek communicator. But science fiction doesn't only inspire gadgets, it also influences how we think. Books and films help scientists ask better questions. They imagine problems we haven't yet faced and offer strange creative ways around them. They push the edges of what seems possible, and sometimes those ideas plant seeds in real research. The idea of a warp drive, for example, started as a fictional engine that let spaceships move faster than light. But in the 1990s, a physicist named Miguel Alcubierre proposed a real version based on Einstein's equations. It's still entirely theoretical. It would require exotic matter and enormous energy, but it exists, not just in a script, but in the pages of physics journals. In a similar way, the concept of artificial intelligence has been shaped by decades of storytelling, from the helpful droids of Star Wars to the thinking machines of 2001, A Space Odyssey. Fiction has painted vivid pictures of how AI might evolve. And while real world AI is still far from those portrayals, the questions they raise about trust, consciousness, and responsibility are guiding how scientists build and manage today's intelligent systems. Sometimes science fiction doesn't lead to invention, it leads to caution. Books like Brave New World in 1984 warned us about surveillance, control, and the loss of personal freedom. Stories about climate change and space colonization invite us to think ahead, to weigh our choices carefully. They hold up a mirror to our ambitions and ask us, is this the future we want? This is what makes science fiction so important. It gives us a sandbox, a safe place to explore dangerous or difficult ideas. It lets us run simulations in our minds before we build them in the real world. It reminds us that progress isn't just about speed or success, it's about wisdom too. And while real science moves slowly through testing, peer review, and careful steps, fiction is allowed to leap. It can guess, it can hope, and sometimes those leaps give scientists just enough courage to try something bold. Even astronauts and space engineers have admitted to being inspired by the shows and books they loved as kids. Some joined NASA because of Star Trek. Some became physicists after reading Asimov or Clarke. These stories light a spark, a tiny thought that says, maybe this could be real. So tonight, as you drift deeper into rest, remember this: that thing you dreamed about as a child, that flying car, that invisible cloak, that starship gliding between galaxies, it might not exist yet, but it mattered because it helped someone, somewhere, imagine a different kind of tomorrow. And imagination is where every great discovery begins, not with numbers or formulas, but with wonder, with the quiet thrill of possibility, with a story that starts, what if, and ends, someday, with we did it, pure fanfic to read the turd, and that well, let's imagine something wild together. What if, just for tonight, we ignored the rules of the universe? What if faster than light travel wasn't just possible, but easy? No complicated energy equations, no problems with mass or time, just smooth, quiet movement beyond the speed of light. What would happen? The first thing to understand is that going faster than light isn't just about getting somewhere sooner. It's not just cutting a 10,000-year trip down to a weekend getaway. It's about breaking the way space and time are stitched together. Because in the world we know, light sets the rhythm. It's how information moves. It's how events stay in order. If you go faster than that, if you outrun a beam of light, then strange things begin to unfold. Imagine you leave Earth at faster than light speed. You wave goodbye, fire up your engines, and zip off toward a distant star. From your perspective, it all feels normal. You're cruising through space. But now imagine someone back on Earth watching you. According to their clock, something odd is happening. You didn't just travel quickly, you may have arrived before you even left. It sounds impossible, but it's what the math says. You see, in Einstein's universe, time and space are woven into a single fabric, space time. When you move faster through space, time bends to balance it. That's why astronauts moving at high speeds age a little slower than those on Earth. It's a real effect called time dilation. But if you break the light speed barrier, the bending gets so intense that time can twist backward. And that's where things get messy. Let's say you send a message to your friend, traveling faster than light. If they respond instantly, their reply could arrive before your message ever left. You would read their answer before you even ask the question. Now imagine using this power for more than just messages. What if you could travel faster than light to any point in space, and in doing so slip backward in time? You could visit the past, change something small, save a life, prevent a war. But then what happens? If your actions change the future, would you still have a reason to go back in the first place? This is called the grandfather paradox, a classic thought experiment. If you traveled back and stopped your grandfather from meeting your grandmother, you would never be born. But if you were never born, you couldn't go back to stop them. And if you didn't go back, they would meet again, and you would be born, which means you could go back, and on it goes. These loops can spin forever. Causality, the idea that cause comes before effect, begins to break. Events don't follow a straight line, they twist, overlap, and cancel each other out. It becomes hard to say what happened first, or whether first even makes sense anymore. Some physicists think the universe simply wouldn't allow it. Maybe something would always go wrong. Your ship wouldn't start, the path would be blocked. The laws of nature would quietly fold in on themselves to keep time safe, like a safety net we can't see. Others wonder if time itself is more flexible than we think. Could there be branching timelines, alternate versions of history, where every choice creates a new path? If you change the past, maybe it wouldn't affect your timeline at all, just create a new one, running in parallel. You wouldn't erase your present, you would step into a different one. This is still deep in the realm of theory, more dream than design. But even as a dream, it shows us how connected everything is. Time, space, speed, cause. Pull one thread, and the whole tapestry shifts. And maybe that's why faster than light travel is so tempting. Not just because it means going farther, faster, but because it means changing what is possible, bending the very shape of reality. But for now, the light speed limit holds. The universe keeps its secrets tucked safely behind that bright, invisible line. Not to tease us, not to punish us, but perhaps to protect the delicate order of things, to keep moments in line, to keep cause and effect gently flowing like a stream that only moves forward. Still, it's fun to wonder, what if, someday, we could whisper to the past, or step into a future no one else has seen? What would we choose to change, and what would we let be? Close your eyes, let your mind drift, and let those questions float gently with you, like stars outside a quiet window, waiting to be explored. Let's slow down for a moment. We've been talking about light, the fastest thing in existence. We've imagined what it would be like to outrun it, to bend space, to twist time. But tonight, let's take a softer turn. Let's ask a quieter question. Why does the universe need a speed limit at all? It's easy to think of limits as frustrating, like a road sign that keeps you from racing ahead. But not all limits are there to hold us back. Some are there to hold things together. The speed of light, roughly 300,000 kilometers per second, is not just a number. It is one of the deepest truths in the structure of reality, a silent rule that helps everything else make sense. Without it, time might not flow the way it does. Events might lose their order, and the gentle logic of cause and effect, the way one moment leads to the next, could begin to unravel. Let's think about that for a moment. In your everyday life, everything follows a pattern. You pour the tea before you sip it. You hear the thunder after you see the lightning. You knock on a door and then someone opens it. That order is part of how we understand the world. It's what lets stories unfold, decisions matter, and memories form. This is called causality, the idea that causes come before effects, that actions lead to consequences, that time moves in a straight line from past to future. But causality is not just a human idea, it is built into the fabric of physics, and the speed of light is what keeps it in place. Imagine if you could send a message faster than light, not just a little faster, but instant. You could shout across the galaxy and be heard before you even opened your mouth. You could receive a reply before you sent the question, and then the question might never be asked. It becomes a loop, a tangle, a story with no beginning, no middle, and no clear end. Without a speed limit, moments could fold over each other. A decision you make tomorrow could affect what happens today. A sneeze in the future could give you a cold in the past. Everything would be connected, but not in a way that makes sense. It would be like reading a book with the pages all out of order. That's not just confusing, it's dangerous for reality. Because if events don't follow a sequence, then the laws of nature start to crack. Cause and effect would be like jelly, slippery, unstable. Nothing could be predicted, and nothing could be trusted. You could win a race before running it. You could drop a glass and then decide not to let it fall, but it's already shattered. And so the universe, in its quiet wisdom, sets a boundary. Nothing moves faster than light, not because it's cruel, but because it's kind. This rule keeps stories straight. It keeps memories reliable. It allows us to know what happened, when, and why. It gives the world a rhythm, a heartbeat, a path we can walk, step by step, without falling into paradox. Even in the wildest parts of the cosmos, black holes, neutron stars, galaxies crashing into each other, this rule holds. Light still leads the way. It draws a bright line through time and space, telling the universe this came first and that came next. And it's not just about physics, it's about comfort. Because deep down, we all want to believe that things happen for a reason, that if we plant a seed, something will grow, that if we say goodbye, the moment happened, that if we remember something, it really was. The speed of light is more than just fast. It's a promise, a way the universe says, this is how we'll keep time, this is how we'll keep meaning, this is how you'll know where you are. So while it may feel limiting, especially to dreamers and stargazers, it's also a gift, a gentle safeguard, and a quiet guarantee that the story of the universe won't fall apart, that your story too will unfold in the right order, one moment at a time, one heartbeat at a time. So tonight, as you breathe a little slower and the world gets quiet around you, remember light is fast, but the reason it stays that way is simple. The universe wants everything to make sense, and, and sometimes going slower is what makes that possible. Let's picture a single moment. Maybe it's now, maybe it's right where you are, lying in bed, the night soft around you, listening to the quiet rhythm of a voice telling you stories about the universe. Now imagine that moment floating in space and time like a tiny glowing dot. From that dot, light spreads outward in all directions, not in a flat line, but like a growing bubble, reaching forward through time and stretching outward through space. It moves at the speed of light, no faster, no slower. That growing bubble is what scientists call a light cone. It's not really shaped like a cone in the way an ice cream cone is, but if you plotted it on a graph, space going one way, time going the other, it would look like a tall, wide cone rising out of that single glowing dot, a map of what light can reach and when. This idea is at the heart of how we understand time, space, and causality. It tells us what things are close enough to touch us, to affect us, or to even be part of our story. And it gently shows us what lies beyond, not because it's out of sight, but because it's out of reach. Let's slow it down. Right now, the light from this moment, this exact second, is traveling outward. It's rushing away at just under 300,000 kilometers per second, forming the edges of your future light cone. Anything that will ever be touched by the ripple of this moment lies inside that cone. Maybe it's a star a few light seconds away. Maybe it's a satellite. Maybe one day it will be a planet orbiting another sun that receives a distant echo of something you did or said today. These are the things that your present moment could possibly influence, even if only in theory. Now turn the cone upside down. Him, that shape, narrowing toward the point where you are, is your past light cone. It holds everything that could possibly have affected you. Every flash of lightning, every heartbeat of a star, every photon of light that had enough time to reach you. If something lies outside your past light cone, it's too far away. It hasn't had time to reach you, not even at light speed. That means, as far as physics is concerned, it might as well not exist. You can't see it, hear it, touch it, or be touched by it. Not yet. The light cone is how the universe draws boundaries, not with fences, not with walls, but with time. It's how the cosmos decides what can be connected and what must remain separate, at least for now. It's not about power. It's not about size. It's about timing. Even a star 1 billion times the mass of our sun cannot influence you unless it's inside your cone. And that's kind of beautiful, isn't it? It means that influence has a shape, that meaning has limits, that even in a vast spinning universe, your life, your moment, is surrounded by a gentle shell of cause and effect, a space where things can happen and stories can unfold. You are not drifting alone. You are sitting at the center of a web made of light. And yet, outside your light cone, there are still places, still galaxies, still lives. They exist, but not for you. Not yet. Their light has not arrived. Their story has not crossed into yours. And that's not something to feel sad about. It's simply the universe taking its time. Because every second, your light cone grows. More of the universe comes into reach. More of the sky becomes part of your possible future. And maybe, just maybe, one day your ripple will touch something far, far away. A signal, a sound, a moment of kindness, a beam of curiosity, something you send into the dark that someone else might one day feel. The light cone reminds us that connection isn't instant, but it's always expanding. That influence takes time, but it never stops moving. That even the quietest moment, like this one, is reaching outward, softly but surely, through the fabric of space. So tonight, as you lie there, think of your light cone, think of the gentle boundary it draws around you, and the endless beauty just beyond, waiting its turn to arrive. Everything that matters to you fits inside that cone, and everything beyond it is still full of possibility. Why simultaneity depends on perspective, and why that's strangely beautiful. Let's do a little experiment in your imagination. Picture two people standing far apart, one on Earth, one on a spaceship, quietly gliding through space. Each is holding a clock. They both look up at the same moment, or what feels like the same moment, and see a star blink in the night sky. Now ask yourself, did that star blink for both of them at the same time? It's a simple question. It feels like the answer should be yes. After all, it's just a blink, a single moment, a now. But the universe, it turns out, doesn't agree. Because in the world of physics, there is no single universal now. There is no shared ticking clock that tells the whole cosmos what time it is. Instead, time bends. It flows differently depending on where you are and how fast you're moving, and that means now is no longer a shared moment. It becomes personal. Einstein called this idea relativity of simultaneity. It means that two events that seem to happen at the same time for one person may not seem simultaneous to someone else who is moving. Just a small shift in speed or position can change the order of events, not just how you see them, but when they actually occur in your frame of reference. It's not a trick of the eyes, it's a deep truth about space and time. Let's bring it closer to home. Imagine you're sitting still on a park bench, sipping tea, watching two lights flash on opposite ends of a field. To you, they blink at exactly the same time. But now imagine a friend jogging past. To them, the light ahead might seem to flash first, while the one behind flashes second. You're both right. Neither is wrong. You just have different versions of now. And here's where things get even more curious. And in everyday life, these differences are too tiny to notice. We don't live fast enough or far enough apart for them to show up. Our world feels stable, shared, predictable. We make plans at 8 o'clock. We celebrate New Year's at midnight. We tell stories that begin, then move forward in time. But the universe plays by bigger rules. Out among the stars, where distances stretch for billions of kilometers and speeds reach close to light itself, time doesn't stay still. It dances, it twists, it chooses favorites. And so now becomes a suggestion, not a command. That might feel unsettling, like the rug has been pulled out from under your feet. But take a breath, let it sit for a second, because maybe it's not such a bad thing. Maybe it means that each of us carries a little piece of time with us, that our journey, our movement through the cosmos, helps shape how we experience the world, that your now is like a fingerprint, unique, unrepeatable, yours alone. And maybe, just maybe, that's beautiful. It means the universe isn't a rigid clock, it's a living, flowing thing, a cosmic symphony where each part plays its own rhythm. No conductor waving a baton, just moments unfolding, one after the other, in a harmony that changes depending on where you are standing. It also means that connection is a kind of miracle, that night and light are unprolifer, that when two people meet, or two voices share a laugh, or two lights blink in sync, it's not because time is fixed, it's because time allowed their paths to cross. Their now just happened to line up, even if only for a moment. And then it moves on. So tonight, as you rest your head and close your eyes, remember this. There is no single now that rules the stars, no cosmic clock ticking down the seconds for everyone at once. Instead, there are countless little nows scattered like lanterns across the sky, each glowing quietly in its own corner of time. You are one of them. Your now is real. It is yours. And though it may not be the same as anyone else's, it still matters. It still shines. It still fits perfectly into the bigger story the universe is writing. So as your own moment stretches forward, softly and slowly, into sleep, let go of the need to hold time too tightly. Let it drift. Let it ripple. Let it be yours. Because even in a universe without a single shared now, you are never truly alone. You are part of the rhythm. And somewhere out there, in another moment, another person is dreaming too. From streaming to texting, how fiber optics and light pulses make it all possible, make it all possible, make it all possible. And remember to check for right now, in this quiet moment, whether you're curled up in bed, watching shadows dance across the walls, or listening with your eyes gently closed, something extraordinary is happening just a few inches away from you. Maybe your phone is resting beside you. Maybe it's in your hand, gently glowing, carrying this very video to you. It looks calm on the outside, just a rectangle of metal and glass, but behind the screen, it's whispering with light. Yes, light. The same thing that streams from the sun, glows from the stars, and shimmers off your favorite candle flame is also at the heart of your phone's connection to the world. Every text message you send, every picture you scroll past, every sleepy science video you stream on a quiet night, all of it relies on bursts of light, traveling at nearly 300,000 kilometers per second, the speed of light, through hair thin strands of glass called fiber optics. Let's slow it down. Brewel does questionable tonguering. Imagine your phone wants to send a message. Maybe it's a simple good night to someone you love, or maybe it's reaching out across the world to request this very video from a distant server. To do that, it needs help, not just from the phone towers you see on hills or rooftops, but from the vast web of glass fibers buried beneath our cities, under the oceans, and across continents. These fibers are thinner than a human hair. Inside, pulses of light bounce from one side to the other, traveling long distances without ever escaping. They don't spill out into the ground or sky. They stay neatly trapped, guided by total internal reflection, like light caught inside a mirrored tunnel. Each of those light pulses carries information, not in colors or pictures, but in rapid flashes, a kind of Morse code made of brightness and silence. On, off, on, off, millions of times per second. It's invisible to us, but to machines, it's a conversation. And it's fast. So fast, in fact, that messages can travel from one side of the planet to the other in the blink of an eye and still have time to circle back again. This is the quiet magic of fiber optics. And while your phone might also use wireless signals to connect, like radio waves or microwaves, much of the journey still depends on light, especially once your message leaves the tower and heads toward its destination. Somewhere along the way, it almost always becomes light. And it doesn't stop there. Every time you send an email, scroll through photos, or watch your favorite sleepy scientist talk about physics and dreams, you are tapping into an invisible web of light, a global network that hums just beneath our feet. Each connection is powered by lasers, firing in patterns too fast for the human eye to catch. Each piece of data is turned into light, sent across glass, and turned back into information at the other end. It's so fast and so seamless that we barely notice. And yet, it's happening all the time. Every hello, every map direction, every lullaby streamed through a speaker while you drift off. All of it carried on waves of light that were once reserved for stars. Think about that for a moment. The very same phenomenon that lets you see the moon or glimpse the shimmer of a firefly in summer is also how you stay in touch, stay informed, and stay entertained. Light doesn't just illuminate the world, it connects it. And here's something even more beautiful. Light travels without touching. It doesn't need wires or roads or carriers on horseback. It moves gently, effortlessly, weaving the world together with silence and speed. It carries laughter across oceans. It brings comfort from distant voices. It tells stories in the dark. Right now, this video, these very words, might be flashing through fibers beneath sidewalks, under rivers, even deep below the ocean floor. A wave of light stretching toward you, blinking out the quiet rhythm of science, curiosity, and care. All so you could listen, rest, and wonder. So the next time you pick up your phone, pause for just a second. Think about what it's doing. Not just lighting up your screen, but connecting you with the help of light to places far away, to people you love, to ideas, to questions, to stories shared under blankets, or whispered into pillows, or softly told on a night just like this one. And all of it made possible by a thread of light dancing quietly through the dark. How light speed and relativity keep you from getting lost, and when certainty affects. You might not think of Albert Einstein when you're finding the nearest coffee shop, but every time you open your phone and tap that little blue dot on a map, every time you ask your GPS to guide you home, or track a delivery, or help you find a hiking trail, you are quietly relying on one of the most brilliant minds in human history. And you're also trusting something else, light. Because let's take a gentle wander through how it all works, and how, without Einstein's ideas and the steady speed of light, we'd all be very, very lost. First, what is GPS? A mad purity acid anteratrice piena. It stands for Global Positioning System, and it's made up of over 30 satellites orbiting high above Earth, circling the planet twice a day. These satellites don't just float, they each carry extremely precise atomic clocks, and they are constantly sending signals down to the ground, tiny radio pulses that say, "Here I am, here is the time." Your phone listens to these signals, not just from one satellite, but from several at once. By comparing the time each signal arrived, your device can figure out how far away each satellite is. And with that information, it can pinpoint where you are, sometimes within just a few feet. It sounds simple, but hidden underneath is something truly wild. Each of those signals is a message that travels at the speed of light, about 300,000 kilometers per second. That means even a tiny mistake in time, just a millionth of a second, could mean hundreds of meters of error. Your blue dot might not be on your street, it might be in another city, so everything has to be perfect. And here's where Einstein comes in. He discovered that time is not absolute. It does not tick the same for everyone. Instead, time flows differently depending on how fast you are moving and how close you are to gravity. This is the heart of his theory of relativity. His Now imagine a GPS satellite zooming around Earth at over 12,000 miles per hour, about 20,000 kilometers above your head. It's moving fast, and it's high up, farther from the pull of Earth's gravity. According to Einstein, both of those things change the way time ticks on that satellite. From our perspective down here, time on the satellite actually moves a little differently. Its clock runs slightly faster because it's farther from gravity, but it also moves slightly slower because of its high speed. And guess what? Those tiny changes, that bending of time, are just enough to throw everything off. If we didn't account for Einstein's equations, GPS systems would drift by about 10 kilometers every single day. Your maps would become completely useless. Your delivery might end up in a river. You might be told to turn left into a tree. But we do account for it. Every satellite is programmed with the math of relativity. Its clocks are adjusted, balanced, and corrected so that what your phone receives is as accurate as possible. Thanks to Einstein, your blue dot knows where to go. It's strange to think about, isn't it? That a century old theory about space and time, one that once seemed abstract and unreachable, now helps people navigate rush hour traffic. That every time you follow directions, find a friend's house, or track a weather balloon, you're living inside Einstein's math. Even more incredible, it all works because light moves at the same speed, no matter what. That's what allows your phone to measure distance using the timing of those signals. Without the constant, unwavering speed of light, this beautiful system would fall apart. GPS is a kind of quiet miracle, a ballet of light and time and space, unfolding above us every minute of the day. It blends physics and engineering, satellites and science fiction to help us find our way. And the best part? You don't even have to think about it. It just works. If you So tonight, as you drift towards sleep, think about that little blue dot, the one that finds you in a city full of streets, the one that guides planes through clouds, the one that lets farmers plant with precision and hikers explore without fear. That dot is a message sent at the speed of light, touched by relativity, reaching from the stars to your pocket. All because Einstein looked at the universe and asked, what if time isn't the same for everyone? And all because light, silent, steady, impossibly fast, carries the answer to that question through space every single second. Light's role in vision, sleep rhythms, and the daily rise and fall of melatonin. Your eyes are always watching for it, even when you are not paying attention. Light. Big. It's more than just something you see. It's something your body listens to, something your brain depends on, something your whole rhythm is built around without you even noticing. And just like every other part of the universe, even your eyes obey the limit, the speed limit of light. Wha- Let's slow things down and take a gentle walk through what that means, starting with the simple act of seeing. Right now, light is bouncing off everything around you: the soft curve of your pillow, the quiet shape of your ceiling, maybe the screen in front of you, glowing gently in the dark. That light travels from those surfaces to your eyes at a speed faster than anything else in the universe. It takes just a tiny fraction of a second for it to reach you. And yet, that tiny moment means everything. Inside your eye, the light hits your retina, a delicate layer of cells at the back, filled with little sensors called rods and cones. Some respond to brightness, others to color. They don't think or feel, they just catch the light and turn it into signals, which then travel along the optic nerve into your brain. There, a small miracle happens. Your brain builds a picture, a whole world, a sense of space, color, motion, and meaning, all from light arriving at the back of your eyes. But that's not all light does. It doesn't just let you see the world, it helps you know when to sleep, when to wake, and how to move through your day. Tucked deep in your brain is a tiny cluster of cells called the suprachiasmatic nucleus, a long name for something about the size of a grain of rice. But this little grain is your master clock. It keeps track of time inside your body, not with gears or ticking hands, but with chemistry. And what it listens to, more than anything else, is light. As morning light pours in through your eyes, it tells your clock that the day has begun. The brain gets the message and starts to lower your melatonin, the hormone that makes you feel sleepy. You feel more alert. Your body temperature rises. Your heart beats just a bit more quickly. You start to move through the rhythm of being awake. And as night comes and the light fades, the message changes. Darkness returns. Your brain begins to release melatonin again. It's like a slow wave of drowsiness washing over you, inviting you to rest. Your breathing softens, your muscles relax, and soon your eyes close once more. All because of light, and all because of how fast it gets to you, how precisely it triggers the cells in your eye, how quickly those signals reach your brain, how perfectly they keep your internal world synced with the external one. Even in total darkness, your body remembers what light was doing before. That's why screens can sometimes confuse your rhythm. Bright blue light in the evening, like the glow of a phone or tablet, can fool your brain into thinking it is still daytime. It can hold back the release of melatonin, make it harder to fall asleep. That's why dimming your lights and stepping away from screens can help your body remember that it is nighttime. It's not about rules or routines. It's about listening to the signals that light is sending you, soft and silent, but incredibly powerful. And here's a lovely thought. When you gaze up at the moon, or into a candle's flicker, or even just watch sunlight dancing on a wall, you are feeling the same light that helped guide life on Earth for billions of years, the same light that plants reach for, that birds follow on their journeys, that sets our clocks and shapes our dreams. Your eyes are little light detectors, always tuning into what the world is doing, always obeying the limit, that silent universal speed to bring you a sense of now. So tonight, as your melatonin gently rises and your eyes begin to close, know this: the light may be fading, but it has already done its job. It has helped you see, helped you feel, helped you understand your place in time. And now, with the world going quiet around you, your body shifts into rest, all thanks to something that raced across the room at the speed of light and whispered, "It's time to sleep." How light powers life itself. one photon at a time. Light doesn't just help us see, it feeds the world. Better develop a taste for fermented milk. Better develop a taste for pate. Better develop a taste for pate. Better develop a taste for pating born in sleep. Better develop a taste for pate. Better develop a taste for pating born in. Every green leaf, every blade of grass, every tree reaching toward the sky, they are all catching something invisible and turning it into life, one tiny particle at a time. That invisible something is light, or more precisely, photons, the little packets of energy that make up light. And when a photon touches a leaf, it begins one of the most important processes on Earth, photosynthesis. It's a soft word for a mighty act, a quiet partnership between plants and light that makes almost everything else on our planet possible. Let's take a gentle wander into how it all works. Imagine a single ray of sunlight drifting down through the sky. It travels across space at the universal speed limit, racing from the sun to Earth in just over 8 minutes. It slips past clouds, weaves between air molecules, and finally lands on the wide green face of a leaf. Inside that leaf, tiny green structures called chloroplasts are waiting. These chloroplasts are filled with chlorophyll, the pigment that gives plants their green color. But color is just the beginning. Chlorophyll has a special talent. It can catch photons, and when it does, something magical happens. The energy from the photon gets absorbed, not just reflected or warmed, but taken in like a spark. That spark of light kicks off a chain reaction. The plant begins to take carbon dioxide from the air and water from the ground, and it uses the light's energy to rearrange them into something new. Glucose, a kind of sugar, a kind of fuel, and as a bonus, the plant releases oxygen, the very air we breathe. So every breath you take, every bite of fruit, or grain or vegetable, is part of this gentle, powerful exchange. Light becomes food, light becomes air, light becomes life. But it doesn't stop with plants. When an animal eats a leaf, or a piece of fruit, or even another animal that once ate plants, that energy that captured photon gets passed along from one cell to another, from sunlight to salad to squirrel to you. We are all part of that chain. Even the cells inside your body use a kind of photosynthetic inheritance. The glucose made by plants gets broken down in your mitochondria, the tiny power stations inside your cells, to make energy, energy you use to move, to think, to dream, energy that began its life as a particle of light. All around the world, every forest and field is quietly harvesting sunlight, not with noise or machines, but with stillness, with patience, with leaves that flutter gently in the breeze, catching photons like hands catching raindrops. Even under the sea, this process continues. Tiny algae float near the surface, doing the same work, feeding fish, feeding coral, feeding entire ecosystems, all powered by light, and all made possible because photons travel fast enough and reliably enough to reach us in just the right form. If light moved slower or had a different kind of energy, this delicate process might not work at all. But it does, and, and it has for billions of years. But yet, photosynthesis is not just a survival trick, it is a planetary rhythm, a dance between sun and soil, between air and life. Every forest you walk through, every garden you pass, is a soft chorus of chloroplasts doing their ancient work. Even now, as you listen to this and prepare for sleep, somewhere a tree is drinking in the light. Somewhere a flower is turning photons into petals. Somewhere a field is filling with quiet meals made from sunlight. It's humbling to think that your next meal may begin not in a kitchen, but on a leaf, that the energy in your fingertips once came from a ray of sunshine that traveled millions of kilometers just to touch the earth. We are, in a very real way, made of light. So the next time you sit down to eat, or take a breath of fresh morning air, or walk through a patch of grass, remember the silent work that made it possible. Remember the leaf, the chloroplast, the photon, and the quiet miracle of a sunbeam turned into sugar. And tonight, as the world dims and your eyelids grow heavy, know that even in the darkness, the memory of light remains, stored in every cell, every breath, every gentle heartbeat. Sleep well, little photon catcher. The garden will be waiting in the morning. The circadian rhythm and its deep relationship to shifting sunlight. Even if you lived in a cave, even if you had no clock, even if you never saw the sun again, your body would still try to keep time. Deep inside you, there's a quiet rhythm ticking away, a gentle cycle that rises and falls over the course of a day. It's not set by your phone or your alarm clock, it's set by light. This rhythm is called your circadian rhythm, from the Latin circa diem, which means about a day. And it's one of the most ancient, most trusted systems your body depends on. It tells you when to sleep, when to wake, when to eat, when to heal, and even when to dream. But how does it know? Let's take a slow, gentle journey into the story of your body clock and how the soft rising and falling of sunlight shapes nearly everything you do. Every morning, as the sky begins to brighten, your eyes sense the first traces of light. Even before you're fully awake, even through closed eyelids, a special group of cells in the back of your eyes notice the change. They're not there to help you see shapes or colors. They're there to tell time. These cells send a signal to a tiny part of your brain called the suprachiasmatic nucleus, or SCN for short. It's only about the size of a grain of rice, but it acts like the master clock for your whole body. When light hits the SCN in the morning, it starts a cascade of instructions. Your brain tells your body it's time to be alert. Your temperature begins to rise. Your heart beats a little faster. Hormones like cortisol gently lift you out of sleep. As the day unfolds, the rhythm continues. Your body prepares for movement, digestion, learning, and problem solving. Everything flows in tune with the light. Then, as the sun starts to set and light fades, the signals shift again. Your body begins winding down. Your brain releases melatonin, the hormone of darkness and rest. Your muscles relax. Your thoughts slow. You get sleepy. This isn't just a suggestion, it's a deep, ancient instinct. Humans evolved under a sky that always told them what time it was. Bright bluish light in the morning said wake up. Warm orange light in the evening said rest. But now, things have changed. We live in cities that never sleep, rooms that stay bright long after sunset, screens that glow just inches from our faces, and your body still listens to light, even artificial light. That phone you scroll before bed, or the bright ceiling bulb in your kitchen, can confuse your clock. It might tell your SCN that it's still daytime, even when your body is begging for sleep. That's why sleep experts suggest dimming your lights in the evening, using warm tones, and giving yourself time away from screens before bed. It's not just about getting more rest, it's about helping your body find its natural rhythm again. Even animals follow this rhythm. Birds sing at dawn, not just because they're awake, but because their internal clocks tell them it's the right time to speak. Flowers open and close with the light. Sea creatures rise and fall in the water as the day changes. We are all timekeepers. Your organs, your liver, your stomach, your lungs all have their own mini clocks too. And they take their cues from the master clock in your brain. If the rhythm is thrown off by shift work, long flights, or irregular sleep, everything from digestion to mood to memory can feel a little out of sync. But the beautiful part is, the body always wants to find balance again. Give it a few mornings of sunlight, a few nights of calm darkness, and it will start to realign. The rhythm returns. So, tomorrow morning, when you open your eyes, try to take in some real daylight. Step outside if you can. Look up. Let that first burst of morning sun wash over your face and send its message to your sleepy brain. And at night, let the darkness in. Let your room soften. Let your mind settle. You are not just reacting to the world, you are in harmony with it. Like the tide follows the moon, like petals follow the sun, your body quietly listens to the light. It tells time by it, it heals by it, it lives by it. So tonight, as your rhythm guides you gently toward rest, know this: you are part of something ancient and beautiful, a living clock ticking softly in the dark, waiting for dawn to return. How all forms of electromagnetic waves, light's extended family, shape modern life. Light has a family, and it is a very big, very talented one. When we think of light, we usually picture what we can see: the warm colors of a sunset, the glow of a light bulb, the sparkle of stars. But visible light is only a tiny part of something much larger. An entire spectrum of waves moves through our world every second, seen and unseen, loud and quiet, powerful and gentle. This family is called the electromagnetic spectrum, and light is just one sibling in a house full of wonders. Let's start small. Gamma rays are the smallest and most energetic members of the light family. They're not the kind of light you want to get too close to. Born in the hearts of stars and the collapse of atoms, gamma rays are used to treat cancer and study the farthest reaches of space. They carry energy so intense they can pass right through most materials, and yet they are still part of the same family as the gentle sunlight that warms your skin. Next come X rays. You've probably met them at the dentist's office or in a hospital room. They're a little less powerful than gamma rays, but still strong enough to see through skin and soft tissue, revealing the solid bones beneath. X rays give us a superpower: the ability to look inside without cutting anything open, and they've saved countless lives because of it. Then come ultraviolet rays, the kind you feel on a sunny beach when you forget sunscreen. They're invisible, just past the edge of violet light. A little UV helps your body make vitamin D. Too much, and you might end up with a sunburn. Bees can see ultraviolet light, giving flowers secret patterns we can't detect. In their world, petals wear invisible signs that guide them to nectar. Then finally comes visible light, the cozy middle child of the family. This is the part of the spectrum that your eyes are tuned to: red, orange, yellow, green, blue, indigo, violet. Each color a different wavelength, each one a gentle wave moving through the air or bouncing off objects to help you see the world around you. Just beyond red light is infrared. You can't see it, but you can feel it. It's the heat coming off a campfire or the warmth of the sun on your face. Infrared cameras can see in the dark by detecting body heat. Remote controls use it to send silent instructions to your TV. Night vision goggles let soldiers, scientists, and wildlife researchers explore the world even after the lights go out. And then we go deeper. The waves get longer, and their uses even more familiar. Microwaves are next. Yes, the same waves that heat up your leftovers, but they also carry the signals that connect your phone to a nearby cell tower. They bounce between satellites and Earth to bring you GPS directions, streaming shows, and live weather updates. All this invisible traffic flows through the air around you, a silent river of information. And finally, the longest waves of all, radio waves. These are the storytellers. They carry music, news, voices, sports, and secrets across great distances. From giant antennas to tiny receivers, radio waves let us speak across cities, countries, and oceans. Even the sounds of distant stars and planets travel to us as radio waves, and we catch them with massive dishes aimed at the sky. All these waves, from gamma rays to radio waves, are part of one family. They all travel at the same incredible speed, the speed of light. The only thing that makes them different is how long their waves are and how often they wiggle through space. Shorter waves carry more energy. Longer waves can travel farther and bend around obstacles. Together, they form a complete picture of the world. Some waves see the hot, some see the invisible, some hear, some heal. Our bodies, our cities, our skies, they're all bathed in this quiet glow. You don't need to see the waves to know they're there. Every time you flip on a light, heat up a meal, take an x ray, check the weather, or listen to the radio, you're dancing with light's extended family. So tonight, as you lie in bed, you're not alone. Around you and through you, gentle waves continue to move, carrying songs, signals, and warmth across space and time. Every time you look up, you're looking back, a calming meditation on time delay and cosmic patience. Tonight, when you gaze up at the stars, whether it's through a window, out on a balcony, or just in your imagination, you are not seeing them as they are. You are seeing them as they were. That is not a poetic idea, it is a scientific truth. The light that reaches your eyes from those stars has been traveling for years. For some stars, just a few. For others, hundreds, thousands, even millions of years. The farther away the star, the older the light. It means every time you look up, you're looking into the past, a soft kind of time machine. Light, even though it moves incredibly fast, almost 300,000 kilometers every second, still takes time to cross the immense distances of space. And because the universe is so vast, even something that fast cannot outrun the hugeness of it all. Take the sun, for example. It is the closest star to us, just over 150 million kilometers away. That light takes about 8 minutes to reach us. So when you feel the sun on your skin or see a sunrise light up the sky, you are feeling warmth that left the sun 8 minutes ago. If somehow the sun blinked out, vanished in an instant, we would not know right away. For 8 full minutes, the earth would still glow with sunlight, unaware. Now, stretch your eyes farther to the twinkling points of light in the night sky. Many of those stars are dozens, hundreds, or thousands of light years away. A light year is not a measure of time, but a measure of distance, how far light can travel in a year. So if you are looking at a star that is 500 light years away, you are seeing light that left it 500 years ago. That starlight began its journey when people still rode horses, lit homes with candles, and dreamed of flying machines. And yet, that ancient light has traveled all that time across a quiet, empty darkness just to arrive in your eyes tonight. It has not faded. It has not missed a step. It simply moved, second by second, straight toward you. The stars are always sending out light. Some are already gone, their fires burned out long ago. but their light is still on the way, still crossing space, still part of the sky you see. In that way, the universe holds on to memory. It does not forget the shine of things that once were. This time delay is not a flaw, it is a gift. It lets us look back to see galaxies as they once looked, to study the early days of stars and nebulae. Telescopes become historians, astronomers become time travelers, and we, just quiet observers, get to witness the oldest light of all, the glow of the cosmic microwave background, a whisper from the birth of the universe itself, still reaching us more than 13 billion years later, faint, stretched thin by time and distance, but still here, still speaking. When you stare up at the night sky, you are not just looking at space, you are looking at time, a sky full of yesterdays, arranged gently overhead. It reminds us that the universe is patient, that light, no matter how long the journey, always arrives, that even things separated by enormous distance are still connected if we are willing to wait. You do not need a telescope to feel this connection, just your eyes, your breath, and a little bit of wonder. There is something deeply calming in the idea that the light shining down on you tonight has been traveling for ages, and yet here it is, finding you. A soft reminder that in the grand, quiet rhythm of the cosmos, things take time. Signals take time. Understanding takes time, but they come. So next time you look up, take a breath. Let it be a pause, a moment of stillness in your day. You are not just looking at stars, you are looking at stories, each one glowing with the light of a moment that once was. Let it remind you that all things, even starlight, arrive in their time, and you are right on time to see them. Introduce the cosmic microwave background, the earliest whisper of light still glowing around us. Not all light is bright. Some of it hums softly, stretched thin across the sky, too faint for your eyes to see, but it is there, all around you, filling the universe like a quiet memory that never faded away. This soft light is the oldest we know. It is called the cosmic microwave background, or CMB for short, and it has been traveling through space for over 13 billion years. To understand where it came from, we have to go back to the very beginning. Imagine the universe when it was brand new, not filled with stars or galaxies or anything familiar, just a hot, dense soup of particles and energy. It was crowded, chaotic, and glowing with unimaginable heat. This was the universe just moments after the Big Bang. At that time, light could not travel far. Every time it tried to move, it would bump into something, electrons, protons, floating bits of matter. It was trapped in a haze, like headlights in a thick fog. But the universe was expanding, and as it grew, it cooled. About 380,000 years after the beginning, a blink really, in cosmic time, the universe reached a gentle tipping point. It had cooled just enough for things to change. Electrons began to settle down and join with protons, forming atoms, mostly hydrogen. Suddenly, the fog lifted. For the first time, light was free to travel. And travel it did. That first light, released into the newborn universe, has been on the move ever since, stretching and softening as the universe expands. What began as a hot, blinding glow has cooled into something quiet and calm, a gentle microwave whisper that still drifts all around us. That is the cosmic microwave background. You cannot see it with your eyes, but special instruments can. And when scientists first discovered it in the 1960s, almost by accident, it was a revelation, a quiet echo from the past, proof that the Big Bang had happened. A snapshot of the universe in its infancy, still glowing after all this time. Today, we have mapped it in incredible detail. Satellites like Kobe, WMAP, and Planck have helped us paint a picture of this ancient light. And what it shows is more than just a glow. It reveals tiny ripples, slight differences in temperature that later grew into everything we see: galaxies, stars, planets, people. All of it began in those soft patterns. So, in a way, that whisper of light is a kind of baby picture, a portrait of the universe before it even had stars. It tells us what the universe was made of, how fast it was expanding, how old it is now. It is one of the most important discoveries in science, not because it's flashy or loud, but because it is so quietly honest. It simply shines. Even now, when you stand in an open field or sit quietly in your room, that ancient light is passing through you, gently, silently, always. It reminds us that light is more than what we can see, that the universe keeps its own record of time, that long after the brightest events have faded, something still lingers, something patient, and something true. Boy, the cosmic microwave background is not like sunlight or starlight. It is not a flicker or a flame. It is a steady presence, soft and stretched, older than anything we've ever touched. And that makes it oddly comforting, because even in the vastness of space, across billions of years, light endures. It might change shape, it might cool, but it never disappears. So the next time you wonder how far back we can look, or how much the universe remembers, think of that quiet light still glowing in every direction. Not loud, not lost, just waiting to be noticed. And maybe, just maybe, it's the universe's way of saying, I remember, a poetic reflection on the journey of a photon and the stories it tells. If light could speak, what would it say? Would it tell you about the moment it was born, not from a flame or a bulb, but from the heart of a distant star, pulsing with quiet energy in the cold vastness of space? Would it whisper about the time it burst forth after billions of years inside that star, finally breaking free to travel across the cosmos, just for the chance to be seen? A single photon, the tiniest packet of light, begins its journey without a map. It does not choose its path. It has no eyes, no ears, no plans, and yet it moves with perfect purpose, straight, constant, unstoppable. It does not rest, it does not get tired, and it never looks back. Some photons travel only inches, bouncing from your screen to your eyes right now. Others set out across unimaginable distances. They leave stars so far away their names have not yet been spoken. They glide through nebulae and clouds of ancient dust. They pass by planets and moons that may never be touched. They drift past galaxies that will never know we are here. For billions of years, they move, and when they arrive, maybe landing on a telescope's mirror or brushing gently against the back of your eye, they bring with them a message, a quiet story from a faraway time, a picture frozen in motion, a soft reminder that something once happened and that something is still happening, even now. Light does not carry sound, but if it did, perhaps it would hum softly as it moved, a tone just beneath hearing, the music of memory itself. If light could speak, maybe it would tell you about Earth too, about watching oceans shimmer and leaves turn golden, about dancing across mountain tops in the early morning and warming a child's face through a window. It would remember flickers of candlelight in ancient temples, the glow of fires shared by early humans, the sparkle of glass in a scientist's hand, the soft pulse of a satellite orbiting above, the glow of a flashlight under a blanket as a child reads their favorite story one more time before sleep. It would tell you that every moment it touches something, it becomes a part of that moment. It leaves a trace, a warmth, a memory. Even if no one notices, it's there, marking time in quiet beams. Light does not age the way we do, but it knows time. It stretches as it travels. It slows down when it passes through glass or water. It waits patiently, moving at the same pace it always has, no faster, no slower. It is steady, reliable, and deeply loyal to the laws of the universe. If a photon could look back on its life, maybe it would not feel proud, or tired, or old. Maybe it would feel grateful, grateful to have shown someone the face of a loved one, to have carried the colors of a sunset across the sky, to have helped grow a tree, or bloom a flower, or guide a spacecraft, or simply brighten a path in the dark. If light could speak, maybe it would say, I have no voice, but I have always been here. I see without eyes. I move without feet. I carry no weight, yet I hold entire galaxies in my journey. I am what lets you see, what lets you know, what connects you to the past. I am the quiet traveler, the invisible thread between stars and stories. You may not notice me, but I see you. Every moment you have ever known, every book you have ever read, every sky you have ever watched, every face you have ever loved, came to you because of light. So tonight, if your room is dark and your thoughts are quiet, imagine a single photon drifting gently through space. It has traveled far, it has seen wonders, and now it has arrived. It touches your eyes. It tells you, I made it. And in that moment, you are not just looking, you are receiving a message, older and grander than words. A story only light could tell. A gentle philosophical pause. Maybe the universe moves at just the right pace. And we talk a lot about speed, about going faster, getting there quicker, shaving off seconds, gaining the edge. Our world spins with urgency. Fast food, fast lanes, instant replies. It can feel like if you are not racing, you are falling behind. So it is no surprise that we dream of moving faster than light, of pushing past the edge of what is possible, of finding a shortcut to the stars. There is something deeply human about that, a quiet ache to outrun limits and reach what is always felt just out of reach. But what if, just for a moment, we asked a softer question? What if we do not need to go faster? Light, the fastest thing we know, is not loud. It does not boast. It moves steadily, calmly, and without panic. It takes over 8 minutes to reach us from the sun. That is not instant. It is patient. It waits. And still, every morning, it arrives exactly when we need it. The stars we see in the night sky have been shining for millions, sometimes billions of years. Their light is old. It left long before our world had cities or books or names, and yet it reaches us now in the quiet moments before sleep when the world is still. It takes its time, and we are better for it. Maybe the universe does not rush because it does not need to. When we look at galaxies moving apart, or clouds forming stars, or tectonic plates shaping mountains, none of it is in a hurry, and yet all of it changes everything, slowly, gently, unfolding on timescales we cannot hold in our hands. Perhaps speed is not always the goal. Perhaps understanding, connection, and meaning are found not in how fast we move, but in how deeply we notice. A walk under starlight, a conversation unhurried, a single breath taken with awareness. These are not fast things, but they are real, and they stay with us. Even in science, we are learning that some discoveries cannot be rushed. Some questions need to simmer for generations. The patience of inquiry, the willingness to sit with mystery, this too is part of the journey. And think about this. If we could go faster than light, we might lose the very structure that helps us make sense of time, of cause and effect, of memory. Without the boundary of speed, reality starts to fold in on itself. Things happen before their cause. Clocks run backwards. Messages arrive before they are sent. That is not just confusing, it is disorienting. It unravels everything we know. Maybe the speed limit of the universe is not a punishment. Maybe it is a gift. It gives us order. It gives us rhythm. It gives us space to grow. So tonight, if you find yourself wishing you were further along in your goals, your dreams, your understanding, take comfort in this. The universe itself does not sprint. It flows. It unfolds. It waits. You do not need to race light to matter. You are not late. You are not behind. You are moving at the pace of stars being born, of galaxies expanding, of light crossing the universe. That is slow, that is steady, and it is enough. Let the pressure to go faster fall away. You are already traveling through something incredible, a cosmos with its own pulse, its own tempo, its own quiet music. So listen to that rhythm, trust the path you are on, and rest in the knowledge that sometimes the best journeys are not the ones that arrive first, but the ones that let us feel every step along the way. Maybe the real magic is not in going faster, maybe it is in being here, now, exactly where the light has chosen to meet you. Wrap tea with gratitude, calm, and reflection. Rest easy and let your dreams move gently, even if not at light speed. And now, as we reach the end of our slow and starry journey, I just want to say thank you. Thank you for being here, for making time in your night to wonder, to listen, and to drift through a question that has fascinated dreamers and scientists for generations. Whether you are still wide awake or already half asleep, I'm so glad you chose to spend this quiet time exploring the edges of the universe with me. We set out tonight with a simple question: can we travel faster than light? And while the answer is still wrapped in mystery, physics, and possibility, maybe the deeper gift lies in the journey itself, in not rushing, in asking, in imagining what could be. We talked about cosmic speed limits, about the patience of stars, about photons carrying ancient messages across space. And through it all, we were reminded that the universe is not always in a hurry, and maybe we don't need to be either. Right now, as you settle in, feel free to let the last few thoughts dissolve like stardust. Let your breath slow down. Let your muscles soften. You've made it through another day, and that is more than enough. The night is here to hold you, the silence is safe, and the dark sky above is still glowing with light that has traveled lifetimes to reach your eyes. Even if you are not moving at the speed of light, your thoughts, your dreams, and your heart are still part of something vast, something gentle, something beautiful. So tonight, rest easy. Let your mind wander softly. Let your dreams move gently, even if not at light speed. And if you enjoyed this peaceful journey, I would be truly grateful if you gave this video a quiet like or tap subscribe so we can keep exploring the mysteries of science together, one sleepy question at a time. Until next time, dear traveler, may your night be calm, your rest be deep, and your curiosity never stop shining. Sweet dreams from the Snoozy Scientist.